Hello and welcome to lecture 10. So the last thing we learned were these two classic limits. The limit as x goes to 0, sine of x over x is 1, and the limit as x goes to 0, 1 minus sine of x over x is 0. And this allowed us to deduce that the derivative of sine cosine. Now, in a very similar way, using a slightly different trig identity, we have that the derivative of cosine of x is minus sine of x. Check this for yourself. This is a nice little exercise. I like to remember this in the following way. I think of sine as being good because it doesn't introduce a negative sign, and cosine being bad because it introduces a negative sign. They both flip from sine to cosine and back, but sine is good. There's no negative sign introduced. Cosine is bad. We have a negative sign introduced there. Okay, but once we have these guys, then we can find the derivative of any other trig function. So let's do an example. So if we want to find out the derivative of tan of x, tan is just sine over cosine. So we just apply the quotient rule, right? So everything over the bottom guy squared. Differentiate the top guy. Leave the bottom guy alone. Minus. Leave the top guy alone. Differentiate the bottom guy. Right? So we're going to have cosine squared minus minus, which is plus, so plus sine squared. So that's just going to be 1 cosine squared of x, which is sec squared. Cool. And there's a bunch of other trig identities we need to know. So the next most important one is sec of x, which turns out to be sec x tan x. And again, you can just differentiate, apply your differentiation rules, and this will fall out. And that's the best way to get this in your head. Simply do this a couple of times, and then if you're on an exam and you don't remember it, it'll just take you, whatever, 50 seconds to reproduce it. You know? And better to have that, better to know that you can check that this is true, rather than just worry and hope you remembered it correctly. This isn't hard. Just do it for yourself. We need a couple more. We also have the derivative of cot is secant squared minus cosecant squared of x, and the derivative of cosecant squared. So these are more obscure ones. It's possible you might be asked to differentiate one of these guys in an exam, but my guess is that you'll be given this as a formula if you are, because knowing this isn't particularly important. But these four, this one, and obviously sine and cosine, these you absolutely will need to know, right? We don't expect you to need a formula for those. So for sure, know these guys, check that you can differentiate them, recover them, and then you're fine. All right, so once we have them, then we can easily do some exercises. So let's do a really simple, quick exercise. Put it over here. Let's change color. So y x is x squared sine of x. Find y prime. Solution, just apply the product rule, right? Differentiate the first guy, leave the second guy alone. Leave the first guy alone, differentiate the second guy. And that's it. No problem. Yeah? Okay, so what is kind of interesting is how ubiquitous these trig functions actually are in describing the world. And that's because there's this underlying mathematical truth, it's a very profound mathematical truth, and that functions are, in a very natural way, decomposed into frequencies. And sine and cosine are basic frequencies. But let us get to that in a second. First, let's do this exercise, which is as follows. So we have the following scenario. A particle is at the end of a spring. Extended down 5 centimeters from its rest position. Okay. It is released, and then we're going to try and understand its motion, but its function of its motion, of its position, is given by the following. So its position is given by S of t is 5 cosine of t. And our exercise is to find the velocity and the acceleration and then compare that to the physical motion. So find velocity and acceleration. And compare to motion, or compare to physical situation. Okay, so this is a very much idealized physical situation, because what we're imagining is some sort of tabletop, and we have a spring here which is extended 5 centimeters at time 0, and here is our particle. Okay, so this is S of t, and when t is 5, then we are exactly 5 centimeters down underneath the table. Like this. Okay, and it's an idealized situation in that we're going to assume that the spring has got 0 thickness. So when it's not actually being extended, it's 0 thickness spring. Further, we're going to assume that when we let this spring go, it's going to spring back, and it's going to pass through itself and through the table and spring all the way back up to here. Further, we're going to assume there's no mechanical resistance to the spring, no mechanical fatigue of the energy through this process. So it's going to spring all the way back up and go up 5 centimeters above the table. Yeah? Well, this is implicit in describing a motion like this. Okay, so not a very realistic situation, but nevertheless, it's imaginable, right? You can imagine some sort of physical situation where you can create something somewhat similar to this, even if not directly with a spring attached to a table. Yeah? All right, cool. So let's first draw the graph of the motion. So at time 0, we are here at 5. Minus 5 will be here, right? We go down, cross at pi over 2, and at pi we're here. Right? And then we're going to cross again at 3 pi over 2, and we are here at 2 pi. Cool, so this is S of t. And let us take the derivative and see what we get. So S prime of t, I'm just going to differentiate this guy. We're going to have minus 5 sine of t. Okay, so let's plot the graph of this. So normally sine would be going like this, but it's minus, so we're going to go going down, right? So let us this point and this point, so it's going to go down like this, yeah, and then up. And then we're going to be up here somewhere. It's going to go up like this, and it's going to go down. Yeah, that thing is s prime of t, which is the velocity. So put this here, perhaps. This is v of t, the velocity. So that's v of t. Yeah, that's v of t. Right, first, let's think about that. So, let's improvise this glass eraser canister and this to be the table. Go this way. Hope that's somewhat visible. Maybe I move more to the right here. Okay, so we're thinking of this as being the tabletop, okay? And this is actually the height 5 centimeters underneath the table. On the top of my pen here is the particle. So we release it from time 0, okay? Release it from time 0. It's been stretched down 5 centimeters, so it's gonna pull back to its unstretched state. So it pulls back like this, and then the momentum keeps it moving forward, and it's going to go up like this to 5 centimeters above, yeah, and it's going to go down, pass through itself, and go down bottom again. Yeah, time 0 it's here. At time pi over 2 it's here, right, crossing through the table. At time pi it's here, yeah. It's at minus 5, but since the direction is since the positive direction is down underneath the table, minus 5 is above the table. So at minus 5 we're here, and then 3 pi over 2 we're 0 here, and here we are at 2 pi back to where we started. Okay, so that's what's happening. Now let's think about the velocity. So obviously, as we are the obviously, but you have to, if you think about it for a second, you'll realize that the velocity at time 0 is 0 because we've just let it go, right? So it's at rest, we just let it go, its velocity is 0. Yeah? And then what happens? Well, then the spring is pulling back, the tension is being released. As it pull back, then it's going up like this, right? As you think about this more, as the tension of the spring is being released, the spring goes back to its natural state, it's applying a force, and it's applying more and more of a force until it's completely gone back to its natural state of 0 thickness. Yeah? So we start with 0 velocity, then it's going to get faster and faster and faster as this force continuously be applied at it. And then here, all the force has been applied because the spring has gone back to its state of 0 thickness. Right? So here, it's going to have maximal velocity. Yeah? And as we keep going, momentum keeps it going forward, but now the spring is pulling it back, slowing it down, slowing it down, slowing it down until it reaches this height, and this height is 5 centimeters above the table, right? Which is position minus 5 because direction positive is down, right? And here it's being brought to a stop because the spring is being stretched as far as it can go. So now it's going to start to reverse and be pulled downwards again. Yeah? All right, let's think about when we have the maximum velocity. It's going to be when we just cross through the table, right? So that should be the case, that the maximum velocity should be when we cross through the table. And what about the direction of the velocity? Well, downwards is positive. So if we're going upwards, we're going to have negative velocity, yeah? And we're going to have maximal negative velocity at time pi over 2, yeah? And then all the way up here. And now from this point, the string's pulling us back down, now in the positive velocity direction. Positive velocity direction, the maximal velocity will be when we cross through the table again, which will be at 3 pi over 2. Yeah? So we should see maximal negative velocity at pi over 2 and maximal positive velocity at 3 pi over 2. Now let's look at the graph. Sure enough, the maximal negative velocity is right here, yeah, at pi over 2, And it's going with maximal negative velocity of minus 5 centimeters per second. Yeah? And the maximal positive velocity is right here. Yeah? Where it's going at velocity 5 centimeters per second now in the positive direction. Yeah? Do it again. 0, we have negative velocity, which builds and builds and builds. We have maximal negative velocity right here. And the negative velocity gets slowed down to 0. Now we start having positive velocity, more and more, maximum positive velocity crossing here, and then it gets slowed down down to 0. Great, so our velocity that we deduce from differentiating is conforming with our physical intuition of the situation. All right, let us take the derivative of the derivative to find acceleration. So A of t, B prime of t, and if we differentiate this, we're going to have minus 5 cosine of t. Let's put this on the graph, right? So it's exactly negative of the position, right? So it goes like this. Up here, here, here. And this is A of t. Cool. All right. Now, let's see if that conforms with this physical situation. So we now understand the velocity very well, right? So start off velocity 0. Yeah, velocity builds in the negative direction, so it goes more and more negative. Maximal negative velocity slows down to 0. Start having positive velocity, more and more positive. Maximal positive velocity right here, and then slows down to 0. Where would we expect that to be maximum acceleration? Well, if you think about it for a bit, the maximum acceleration is when you have the most force applied to the object. Yeah? Because as you know, in Newton's laws, if you just have an object moving with a constant velocity, that is something which will just continue until you apply some force to change it, right? So in the real world, when you throw something, then it's going to fall down to the ground because gravity will pull it. But if you're in space, just throw something out, then it'll float, right? It'll be directed somewhat by the gravitational pull of whatever planets it's around, or perhaps the sun itself. But nevertheless, it's not going to stop moving until something's done to it. Yeah? And if we had a perfect vacuum and just send something moving, it's just going to continue to move. And you've seen these videos on the space station, what astronauts can just gently throw or just gently let something go, and it'll just keep floating away, right? So we need to have a force to actually change something from its state of velocity to slow it down or to speed it up. Yeah? And the force being applied is the force of the spring. We start with 0 velocity, right? And the spring is applying this, it's applying. Yeah? So we're going to get more and more change of velocity, but the point where it's applying the most change in velocity is actually when we just let it go at the very instant. Yeah? At the very instant we let it go, where we have 0 velocity, we're going to have the most acceleration. So most acceleration is turning it from 0 velocity to something which is actually moving. Yeah? Cool. Let's think about the direction. So we have 0 velocity, but we're going to go in the negative velocity direction because upwards is negative. So we should expect a large negative acceleration. Yeah? And if we look at the picture, that's what we see, a large negative acceleration, setting us the negative velocity direction. Cool. So it's going up here with negative velocity. Yeah? And right here, where it's crossing with the maximal negative velocity, this is where there's the least action of the spring on the particle because the spring's been returned to rest state. So all that's happening here is it's just moving through inertia and a little tiny bit of resistance from the spring as we start to go above. Yeah? A little tiny bit of pulling or adding to the velocity of the spring as we're below. Yeah? So right here, when we have the maximal velocity, we actually have the smallest amount of acceleration. In fact, 0 acceleration will be right here. Yeah? Which is kind of counterintuitive. Well, hopefully it's not counterintuitive to most of you. But many people easily confuse velocity and acceleration. certainly, if you want to go faster, you need to continually add acceleration, but you can be going very fast with no acceleration, of course, and the highest acceleration could be when you have very low velocity. I ride a motorcycle, and I once listened to some video blog of some guy describing his worst motorcycle accident, not because I have a morbid sense of interest in bad consequences for people, just because when I was learning to ride a motorcycle, I thought it'd be good to learn about how things go wrong. And this guy described how he was at a stop sign, and he was on a very powerful bike, and he floored it. He just floored it, and someone else thought they could squeeze by, and so he hit someone else's car with actually very low speed. He hit it like 15 miles an hour, but he'd floored it so much he had a flooring is the wrong word, because you don't put your foot down, you turn the throttle on the motorbike. He throttled it up so hard that he actually hit with huge acceleration, and he was sent flying through the air, 40 meters before he came down, despite having very low speed when he actually hit, which obviously makes sense to us as we have some physical understanding. But it's a little bit counterintuitive. If you tell somebody that you crash at 50 miles an hour, they might think, okay, well, it can't be too bad. Well, it can be very bad. It depends what acceleration you had when you crashed, right? And if you crashed 50 miles an hour with no acceleration, then probably it's not so bad. But if you have a powerful bike and you go from 0 and you just really throttle it as hard as you can, then you can have a very bad situation. Okay, enough of this grim story. Let's go back to this. So we have this guy coming here. When it's maximal speed, it has 0 acceleration. Okay? Continues to move, and now this thing is pulling us down, right? It's pulling us down, so it's decreasing the negative velocity, decreasing it down to its stop here. Right? So here we have more and more acceleration, but now the acceleration is going from having a negative velocity to having a positive velocity. Yeah? So this we would expect to be a positive signed acceleration. Yeah? Sure enough, this happens around 3 pi over 2, and sorry, this is where we cross a pi. This happens here when we're around pi. Start again. This happens when we're at pi over 2. This is where we are around pi, and sure enough, we have a positive acceleration, right? So we're taking this negative velocity, setting it to 0, and then returning us in this direction, which is the positive velocity direction. So we're going down like this, down like this, down like this, down like this, yeah? And then here again is where the spring is having the least influence. Yeah? It's closest to the rest state. So we're going to have 0 acceleration as you cross through the table here, is what we see. And then as we keep going down, keep going down, then this thing is starting to pull us back. So we're going to have less and less positive velocity, right? So therefore, the acceleration will be in the negative direction, slowing us down. And that's what we see coming here in this part. So this is from time 3 pi over 2 down to pi, where we bring it to an absolute end. Cool. Go through this a couple of times. This might take a few times to really see why this works. But it's obviously very relevant to you guys, or to you people, because most of you are engineers. So go through this yourself, go through this explanation, and you'll see that apart from the fact we have a totally unrealistic physical thing, the actual math that we get from differentiating the position to get the velocity and acceleration conforms really nicely with what in the physical world would be happening. You know? And that's a kind of a cool thing. So probably no one's actually seen a physical example of this. I'm not sure I've ever seen a physical example of this, but back in the day, there were these pendulum clocks where you would have this heavy kind of thing, like a pendulum, and it would swing backwards and forwards. And that is how you would count the time. So if you have a very well-made with minimal mechanical resistance set up here, it would gradually ratchet up a notch and count the time. This is another example of this oscillating motion. As you know, this will gradually swing less and less because of resistance and whatever. But it's another thing that's quite well described by a trigonomic function. And even to incorporate the effects of mechanical resistance and air resistance in this. Again, mathematically, it can be done rather nicely, and we can describe this in a very precise way using these kind of things. And overall, as I alluded to before, there is this remarkable, profound fact that arbitrary functions, so just imagine some arbitrary function from 0 to 2 pi doing whatever, it doesn't even have to be continuous, can be understood as a superposition of a bunch of frequencies, which are given by sine of k times t, cosine of k times t as k is different numbers. So if you consider, for example, cosine of 10 times t, then we're going to have whatever 20 up and down oscillations as you go from 0 to 2 pi. So that is very profound and deep fact, and it's the reason that it's actually the reason you're able to watch me right now on YouTube, because the way that images are stored is not by simply okay. So this is how you might think images are stored if you just give it some thought. You might think, okay, well, we have a computer screen, we have pixels, we could put them in order. All right, let's put the pixels all in order, and let's imagine it's black and white picture just to make life simpler, and let's make high numbers very, very dark, very close to black, and low numbers, like say 10 is very close to black, and minus 10 is very close to white. Yeah? Then we could just put a number for each pixel, and that will give a very good kind of representation of whatever pixel, whatever picture you want. And suppose you have whatever, 1,000, I mean, you have much better resolution, but suppose you have 1,000 times 1,000 pixels, then you just need 1,000,000 numbers from minus 10 to 10 to represent any picture. And then you might think, okay, well, what's happening when you send data is that you're sending this string of numbers, this string of 1,000,000 digits through the fiber optic, through the internet. And when your computer gets this string of 1,000,000 digits from minus 10 to 10, it recreates the picture. Yeah? And that might seem like a reasonable thing, except that's not what we do, and it doesn't work, because if you had a bandwidth not ramping up or had different levels of bandwidth, then what could you do? You might think, okay, I'm just not going to send the first 1,000,000 digits, I'll send the first 1,000. But what's the first 1,000? It's just like the first row up here, right? It's going to be meaningless. You send the first 1,000 digits, you can't create anything. It's just a meaningless information. And if you have whatever, the first, not 1,000, but the first, whatever, 10,000, again, it's meaningless. You don't get anything out of it. It's a completely fragile, non-robust way to send information. Yeah? And that's not how images are stored. How images are stored is that they are broken down into their frequencies. So this thing I just described, you can think of it as a function from this plane, this two-dimensional area, into the real numbers. That's multi-variable calculus. And you can decompose it into frequencies in exactly the same way that functions from 0 to 2 pi can be decomposed. And you send this decomposition of frequencies. The list of numbers is the frequency decomposition. This is exactly what a JPEG file is. And that's what you send. And if you can't send all million digits, you can only send 1,000, then that's just sending the first 1,000 frequencies. But you can still recover a pretty good image from the first 1,000 frequencies. And if you want to send the first, whatever, 10,000, then you can recover a better image from the first 10,000. It's an extremely robust system. And it's used all the time. So it's not just used in Netflix and in sending images. It's used sending satellite data down to Earth. Anytime you're transmitting any kind of data where the exact data is not super important, but some level of robustness is, so that if there is some corruption, you still want to get some good information out, then you will send it by encoding into frequencies. And JPEG really was just the simplest encoding into frequencies. It just cut off the frequency at a certain level. And now there are more sophisticated things that do better at recording certain kinds of images. And this is like a big area. But it's using very deep maths and actually quite modern maths if you know, state-of-the-art of signal processing and sending data uses this stuff, uses the fact that we can break things down into frequencies, uses this profound fact that these trigonometric functions are some kind of like atoms, like atoms of all the space of functions in some loose sense. So we are gonna, well, you guys hopefully will learn a lot about trig functions and how important they are. And in this particular, there's a course that we teach called PDE and Fourier analysis. Fourier analysis is the subject I just talked about, breaking things up into frequencies. Where you will learn this stuff, and I hope you will do it because it's really fundamental and it's really part of everyday life. And there's a lot still to be, there's a lot of applications of this stuff still to be worked out. So keep that in mind. It's about 2 years into your future. All right, so let's do another problem. Let's do this problem. Sample. So f of x equals cosine of x. Find f, 27th derivative. Okay, so notation. So f to the n of x is differentiating the function n times. Okay, so find the 27th derivative. Okay, solution. We are definitely not going to differentiate this thing 27 times, right? But let's differentiate it a few times and see what happens. So if we differentiate it once, but cosine is the bad, so we're going to minus sine of x. Differentiate it again. Sine is the good, so we have minus cosine of x. Differentiate it a third time. Now the minus gets killed, we just have sine of x. And differentiate it a fourth time. We're back to cosine of x, right? And then we're back to where we started. So if we differentiate it a fifth time, would be here, minus sine of x. A sixth time here, minus cosine. A seventh time sine, and an eighth time cosine. So we learn that if we differentiate this guy 4k times for any k, then this thing is just equal to cosine again. So write that. Okay, so what are we going to do? Well, we'd like to get to as close to 27 as we can, right? With multiples of 4. A bit of thought will give you that. If we take 24, then that's as close as we can get as multiples of 4 underneath 27, right? Because the next one's 28, which is too big. So we have that the 24th derivative, 24th derivative is cosine. And then we just go down, right? So then the 25th is minus sine. We can just follow that if we don't want to think about it again. 26th is minus cosine of x. Finally, the 27th is sine of x. And that's it. Yeah? Not too difficult. Cool. All right. I'm going to raise the board, and then we'll do some more of this. talk about limits. So let's think about this problem. The limit as x goes to 0 of sine of 7x over 4x. All right, so this isn't of the form that would be easy for us. So we know that this is true. Right? We know this is true. We know, well, why it's true. That's something we're happy with. We don't have exactly that, right? So what can we do? So solution. Let's look at this. 7x over 4x. And I'd like to get it somewhat in the form of sine, something in the brackets divided by whatever's in the brackets, right? So the natural thing to do is to do this. Sine of 7x over 7x, 7x over 4x. Yeah? So long as x is non-zero, then that's the same thing, right? We can just cancel it. Yeah? And if x is non-zero, then the 7x over 4x is just the same as 7 over 4 sine of 7x over 7x. Yeah? And now we're good, because therefore, let's call this thing star. And star, the limit as x goes to 0 of 7 over 4 sine of 7x over 7x. And as x tends to 0, then 7x for sure tends to 0, right? Definitely true. Yeah. So we can pull out this constant, 7 over 4, and this is the limit as x tends to 0, 7x over 7x. And I claim that's just the same as the limit of sine x over x, because x is going to 0. Now, if you're not comfortable with that, if you're not feeling completely happy, what do? You draw a picture. Okay, not sure some kind of tricky stuff is not happening here, messing things up. Let me draw a picture to represent this information. So let me take some very small x. 7x is still very small. So this is our angle. 7x is our angle. And then I remember the explanation of how this limit comes around, right? So we compare this quantity. We have a circle of radius 1. So this side right here is sine of 7x by our trig knowledge, right? And then this little bit of the arc right here is just 7x, because that's what radians mean, right? So we are comparing this side of the triangle with a little bit of an arc, which is almost exactly the same thing, but has a little tiny curve in it. And it gets smaller and smaller. The curve looks more and more like a straight line. And we see that indeed, these two quantities have to be tending towards the same ratio. Let me say that properly, that the ratio of these two quantities is going to be tending towards 1. Right? They're both decreasing, but they're both tending towards 1. And therefore, we expect this thing just to be equal to 1. And it is 1. So this is just 7 over 4. Or you could say, let y be 7x. Yeah? So if 7x goes to 0, then y goes to 0. Then it's the same as saying the limit of y goes to 0 of sine of y over y, which is 1. But that thing is exactly the same as this thing. Yeah? It's exactly the same thing. Yeah? Except this is written in the language of math, whereas this is the pictures. And again, I'd rather you had the picture than you did this. I'd rather you started with the picture. Yeah? And if you're really still not completely convinced, then do some stuff, some algebra with our language of math to confirm that this is indeed the same as this. Yeah? So that's how we get this answer. We turn this unknown limit into something that is like a limit that we understand. All right, let's do another one. See if I remember it. I can't remember it. Okay, let's do another one. let's do limit as x goes to 0 of x cot of x. Okay, solution. Let me change colors just to add to the excitement. So what is cot? I mean, we have limits in terms of sine and cosine, right? So natural thing is to try and turn sine into cot into sine and cosine. So x tangent of x is x, so tangent is sine over cosine, so cot is cosine of x over sine of x, right? And now we start to feel happy because we start to see stuff similar to the limits we know, right? You can write this as x over sine of x of like this, and then multiplied by cosine of x. Okay, so this is how I would hope that you would think about this. This is how I want you to think about this. Okay, so we're taking the limit as x goes to 0. Yeah? We know, because we've understood deeply, that sine x goes to 0, increasingly like x goes to 0. In fact, the ratio of the two tend down to 0. So this thing, I hope you start to recognize, is going to look more and more like 1. Yeah? And as x goes to 0, cosine is just a continuous function. It's just tending towards 1. Yeah? So I hope at this point your intuition, your understanding of the situation, the pictures in your head are saying to you, well, okay, this x is like this little bit of the arc, and this sine is a little bit like this thing. So this is just the ratio of this bigger thing by this smaller thing, but it's really a little bit, just the tiniest bit smaller, and it's getting less and less, tiny bit smaller as x gets closer and closer to 0. So I expect this in the brackets to tend towards 1. That's how I hope you think about this. Yeah? And if you do, then you think, okay, good. So I think I know the answer. I think this in the brackets is 1, and this is 1. Now let's try and confirm this with the math that we know. So we know that when we take the limit as x goes to 0 of x tangent of x, by this algebra we've just done, this is the limit as x goes to 0 of x over sine of x like this times cosine. And what is this? This is the product of two things, product of two functions, right? And we know that when we take the limit of the product of two functions, it's the product of the limit if those limits exist. And those limits do exist, right? So this limit can exist, and certainly this limit exists. Now, just to make sure, when you're a little bit not totally convinced that the limit of x over sine x exists, then just do the following. So look at this. X over sine of x is the same as 1 over sine of x over x. Yeah? So the limit as x goes to 0 of x over sine of x is the same as the limit as x goes to 0 of 1 over sine of x over x. And now we're in the position of a quotient rule because we have a quotient of two functions, the constant function 1 and the function sine x over x. And that limit you for sure know is 1, right? So the limit of a quotient of two functions is the quotient of the limits if both limits exist and the bottom limit is non-zero, which it certainly is. It's 1. So that's just equal to 1 over the limit. This goes to 0, sine of x over x, which is 1 over 1, and we are good. But I would want you to feel really, really happy that the answer is 1 anyway, just because of the picture. This is just the check. This is the check, just to nail it down, but the picture should be very much convincing you this is 1. If you do a free response question, then yes, put down this stuff, nail down your case, make sure no one can complain you haven't answered exactly why things are true. But know why it's true from the picture. Okay, so this thing, the limit is 1. This thing, the limit is 1. Both limits exist. So the limit of the product is the product of the limits. And we have this as the limit as x goes to 0 of x over sine of x. And the limit as x goes to 0, cosine of x, and that is just 1 times 1. And that's it. Cool. All right, let's do another one. This is example 7. Let's change color. Find the limit x goes to 0 of cosine of x minus 1 over sine of x. Okay, solution. All right, so this is how you should think about this. You should think, okay, I know very deeply, I'm very instantly noticing that as x goes to 0, sine of x is very much like x. Yeah? I know that's true. Yeah? And therefore, if I, instead of having this problem, I had cosine of x minus 1 over x, then that's an awful lot like the other limit which I've learned. Right? So you should think, all right, what if we do this? Cosine of x minus 1 over sine of x. I want to use the fact that sine of x is an awful lot like x for small x, and I'm going to do it this way. All right, cosine of x minus 1 over x, x over sine of x. Let's do that. Yeah. And what's the advantage? Well, now we are very much in a position of stuff we've seen before, right? So then this thing, let's call this thing star. And star is the limit as x goes to 0 of those guys, right? So, and just to really sort of make things neater, let's put a minus sign here. So then we're going to have 1. It's exactly of the form of the limit we studied before. And then this thing is x over sine of x. Yeah. Cool. So the minus sign, we can just take it out. It's just a constant. So it's equal to minus the limit. Now these two guys for which the limit exists. The limit of this guy, as we just discussed, is 1, right? The limit of this guy, it's one of the classic limits, the one we talked about in the last class. This thing is 0. So this is the limit of each individual one. They both exist. Times this thing. And this is therefore just 0 times minus 1, which is still 0. Times, let's put it like this, minus 1, which is 0. So the answer is the limit is 0. But this is what we can anticipate anyway, just from looking at this thing right here. Because again, we know that sine of x is very much like x for very small x. And if we just had x here, then this is like minus 1 minus cosine of x over x, which is this limit that we know. Again, the picture for that limit is this. Right? This is cosine here, and then this distance here is 1 minus cosine of x, and we're comparing this x, and we see that it's going to 0 way, way faster than x, and therefore we have this true fact that the limit as x goes to 0 of 1 minus cosine of x over x is 0. Yeah? Cool. All right. So that's how we're going to do trig limits. One way or the other, we have to be able to break them down into limits that we understand. And the way to do that is using these basic facts, these basic things that we are aware of. Q1 being that sine of x is a lot like x as x gets very small. Okay, so that's it for today. I will see the Friday group on Friday.